So the pressure of this coffee is going to be 200 kilopascal. What about this coffee? So that was pure coffee, and I like, the big one, maybe Bentley, about this much. So what's going to be the pressure of this coffee? Could be 100 kilopascal. 100 kilopascal. And that was initially maybe 70 degrees Celsius or 80 degrees Celsius, but let's say that you are standing here, staying here more than an hour. So what's going to be the final temperature of this coffee? The same as the room temperature. So what is the temperature of this coffee? Maybe 20 degrees Celsius. The room temperature is 20 degrees Celsius. And what about this temperature? Also 20, if I leave it like, the hours. So the temperature is 20. So pressure is the same between these two. Temperature is the same between these two. Then what about the volume? What of this coffee? One will be maybe 100 centimeter cube. On the other hand, this one is going to be 200 centimeter cube. Because look at that, the cup is larger than this one, right? So if you want to study this coffee, pressure is going to be the same, okay, no problem. Temperature is the same, no problem. But volumes are not the same. So let's say that, I did the thermodynamic analysis, yesterday about this coffee in this classroom. And it turns out, that it takes about 2 hours to cool this coffee from 70 degrees Celsius down to 20 degrees Celsius. Then if you want to do this, if you do this thermodynamic analysis, and then if the answer is correct, if you buy another coffee and leave it tomorrow, after 2 hours, it's going to be at 20 degrees Celsius. So you know that if you have this particular coffee, it takes 2 hours to cool it down to 20 degrees Celsius. But what about if you buy a coffee as big as this classroom? Then how long it's going to take? The coffee cup is about almost reaching the 30. How long it's going to take? 2 hours? No, it's going to be much, much longer than 2 hours. Why is that? Then the study that I did yesterday is not going to be useful anymore because we have a different volume. So if you want to do a thermodynamic analysis, you want to get rid of this effect because depending on the volume, the result is going to change, right? So the properties who's going to affect the results based on the amount is called extensive property. Those whose values depend on the size or extent of the system. So when you do a thermodynamic analysis, you don't want to use any extensive properties because that the outcome of that analysis is going to change depending on the size of the system, right? Then what is the other property? Then what about this temperature? This small cup is at 20 degrees Celsius. This large cup is at 20 degrees Celsius. So temperature is not related to the size of the system, but the volume is. So temperature is okay. What about pressure? If you have this small cup, pressure is 100. If you have this mid-sized cup, 100. If you have this big cup, is 100 kilopascal. So I can use pressure in my thermodynamic analysis. I can use temperature in my thermodynamic analysis, but I don't want to use this volume in my thermodynamic analysis. So we need to do something on the volume, right? So volume is an example of extensive property, those whose values depend on the size. On the other hand, the temperature and pressures are the examples of intensive property, those that are independent of the mass of a system. So when you do a thermodynamic analysis, you do not want to use extensive properties. You only want to use intensive properties. But still, we need to do something about the volume, because the volume is going to be important in thermodynamics. So what do? We introduce a new property which is called specific property. It's extensive property per unit volume. I'm sorry, per unit mass. So instead of these two volumes, what about if I use specific volume? What is the volume per mass? The volume per mass of this coffee in this small cup may be the same as the volume per unit mass of this big one, right? So we can use specific properties rather than extensive properties. The simple rule convert extensive properties to specific properties is very simple. If you have a volume, you can divide by mass. Then you get the volume per unit mass. In other words, specific volume. So when we say specific volume, just to distinguish between the actual volume and the specific volume, we use lowercase. So this lowercase v represents specific volume. So the specific volume of the coffee in this small cup is going to be the same as the specific volume of any other coffee, as long as it is coffee. So that specific volume is not an extensive property anymore. So it's going to be independent of the size of the system. So we can use this in thermodynamic analysis. So when you have an energy balance equation or mass balance equation or entropy balance equation or any thermodynamic analysis, we prefer using intensive properties and specific properties, not extensive properties. Okay? So whenever, yes. Yeah. So specific volume is volume divided by mass, which is the volume per unit mass. Then how do we know a property is an intensive one or intensive? Very simple. You just divide by and see if you can make specific property. So let's say you have a volume, divide by mass. Then, okay, volume per unit mass, which is specific volume. Makes sense. What about if you have energy? So I have this much potential energy in this coffee, and I'm going to divide by mass. Then what is it? Potential energy per unit mass, which makes sense in physics. What about kinetic energy? Kinetic energy divided by mass is going to be kinetic energy per unit mass. Makes sense. But what about pressure? Pressure divided by mass. Pressure per unit mass doesn't make sense, because pressure is equal between, as long as in the same room, right? What about temperature? Temperature divided by mass. Does it make sense? What is my body temperature? In Celsius, around 36.5. What about your body temperature? Depending on the weight of your stuff, it goes higher or lower No, the temperature should be the same unless you have a fever, right? What about pressure? What is the pressure of my body? The same as the atmospheric pressure. Otherwise, if my pressure greater than atmospheric pressure, then how we get, the bigger and bigger, right? If my pressure lower than the atmospheric pressure, how will get, the shitting. There was a movie a long time ago, like 20 years ago, that all the kids are going downstairs. Yeah, yeah. Anyway, yeah, so that happens. That is possible physically if the body pressure less than the atmospheric pressure. I don't know why I said that, but so there are intensive properties which are independent of mass. We use them in our thermodynamic equation. There are also extensive properties which depends on the mass. We don't use them. We divide them by mass and use their specific properties in our thermodynamic matter. And just to distinguish the actual property and specific property, we use lowercase of the actual property just to, to show that we need a specific property. So if you have energy, this capital E, if you divide by mass, then it's going to be specific energy, lowercase e, energy per unit mass. If you have volume, then you divide by mass, it becomes lowercase v, specific volume. If you have enthalpy that you are going to study later, enthalpy divided by mass, it becomes lowercase h. If you have entropy that you are going to study in chapter 6, divided by mass, you get specific entropy. Okay. So now you will see the difference between capitals and lowercase, right? Any question? Okay. Then let's talk about some specific problems. And per unit volume. We all know about that simple. You already know. What is the inverse of that? Density is mass per unit volume. So the inverse of that is going to be volume per mass. And we just studied it. What is volume per mass? Specific volume. So the specific volume, lowercase v, is the same as 1 over density. And what is the density of water? 1,000 kilograms per cubic meters. Density of water is going to be 1,000 kilograms per cubic meters. That density of water in this classroom is going to be 1,000. What about the density of water on top of mountain Everest? 1,000. That's technically you're right. It should be different, very slight, because the volumetric change due to pressure on a liquid is very small. However, if it is gas like air, yeah, it's going to be significantly different. Because in general, technically, fluids are the volumes of fluid depend on pressure. So liquid volume is going to change depending on the applied pressure. However, in undergraduate thermodynamics or fluid mechanics, we just assume that liquids are incompressible just for convenience. It's yes, the boiling temperature of water depends on temperature. I'm sorry, depends on the atmospheric pressure. So, for example, at 1 atmospheric pressure. So we are going to talk about temperature and pressure relation later, but just for your information, the boiling temperature of water in this classroom, it is close to the sea level. It's going to be around 100 degrees Celsius. But if you go, if you decrease the pressure of the water, then how can you decrease pressure of the water? The simplest way is that just climb up the mountains. So if you go to on top of Mountain Everest, what's going to be the atmospheric pressure? Much less than the pressure in this classroom. So the boiling temperature of water on top of Mountain Everest is going to be less than here. So usually about 50 degrees Celsius. One example that you can also see is that when you take an airplane, like, for a long distance, like, the 8 hours or 10 hours, then they serve you something to eat, right? Are they tasty? No, not at all. Why they are not tasty? Because you're not in the first class? No, they're not tasty because the boiling temperature of water in the cabin of the airplane is less than here. So let's say that, if you want to make a good cake, consider this the cake. Don't eat it, but let's just assume that this is a cake. So if you're a really good chef, you may have a very good recipe. You need to cook them for, let's say, 3 minutes on the stove or something. But if you cook this on top of Mountain Everest for 3 minutes, it's going to be undercooked because the boiling temperature of water, because even though it looks like a solid, it's made of, our body is made of 7% of water. That has a lot of, the water inside. So if the boiling temperature is only 70, when you heat it, the temperature of the meat doesn't go up above 60 degrees Celsius unless it is completely dehydrated. Okay? So if you cook something inside the airplane, the cabin pressure is less than right now here. Therefore, the water is going to boil at lower temperature, much lower temperature than your kitchen. Therefore, whatever the food is going to be, not taste, because you don't want to eat raw food. If you want to cook it like for a long time, let's say that you need to, put this much energy to be fully cooked. If the boiling temperature is less, then you need to cook longer to provide that much heat. If you cook long enough, then the food gets dehydrated and it becomes like, the bacon. Make sense? Have anybody from Denver, Colorado? Or Colorado? Okay, then I can say that. So the Denver, Colorado, it has, the much lower atmospheric pressure. So the boiling temperature of water over there is going to be around 92 to 94. So if you use the same recipe here in Michigan and bring that one to the Denver, Colorado, it's not going to be tasty. It's going to be undercooked. So that's why, if you look for, the Michelin guide, there are not many, the Denver restaurants there. Okay. That's physics. That's engineering. Okay. Then, so that's a side story. Then, if it is really not tasty, when you cook something in an airplane, not necessary. Not necessarily. If you have a private jet, you can increase the cabin pressure, same as here. Then the boiling temperature inside the private jet is going to be the same as here. You can, they have a very nice tasting food. Then why the cabin pressure of the commercial airline is lower than here? Because the maintaining high pressure in a cabin costs a lot of money, and fuel efficiency goes down. So they are trying to, to maintain just not to have any dead body inside. That's why when the airplane takes off, you have a ear pain, right? Because you're inside your eardrum, you have the atmospheric pressure on the ground, but when the cabin pressure goes down, your ear is going to the pop this way, moving this way. That's why you feel the pain. Then what do? You drink something, or you're trying to blow without blocking your nose, right? Then what happens is that there is a tube between the ear and your nose that is called eustachial tube. So you are trying to expand that by drinking water. so the air inside can come out. I know that this is not a medical class, but it's good to know, right? All right, so but we will talk about temperature pressure later. At the end of this chapter 1, we have a the couple of slides, very interesting slides. So until that, let's talk about this intensity problem. Isn't it fun to know thermodynamics? I told you that the chapter 1 and 2 is like the preparing, the playing, the learning about how to play this thermodynamics game. Did I tell you about PlayStation? Did I also tell you that I bought my PlayStation the day before my national insurance exam? That was the biggest mistake I made. So, volume, it's gonna be, it's one of the technical properties. So it is already divided by mass. So it looks like an intensive property, but you can use this one, thermodynamic equation, not the actual volume. And the next one is specific gravity. The ratio of the density of a substance to the density of some standard substance, not the sum. What is the standard substance? Water. Why water? Because water density is pretty simple. 1,000. Pretty simple, right? So we use this one as our, the standard material instead of something else whose density is 3,465 point blah 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 blah. That make your the calculation very the ugly, right? So we use water as 4 degree Celsius as the standard material to determine specific gravity. And the specific gravities of some the common the materials are shown on the right. So how do you use this specific gravity? Fg. You multiply this by 1,000, which is the density of water, to determine the density of the material. So the density of water is 1 times 1,000. 1,000. I don't know why I said that. And the mercury 13.6 multiplied by 1,000, then the density of mercury is going to be 13,600 kilograms per cubic meter. And gold, ice, air, and seawater has higher density than water because the seawater has salt inside, and when you have a minerals inside, their density goes up. Have you seen the people reading a book on a dead sea? Because it's very salty, their density is pretty high, heavy, so you don't have to swim. You just float on the surface. But if you have a cup and then jumping in that the seawater, that's going to be really painful, right? Why is that? Because there is, let's not talk about medical stuff anymore, okay? Then the last one is specific weight. What is specific weight? Such weight is the density times gravity. Then why do we know density? We know gravity. Then why do we combine them to determine another new parameter? Because the density and gravity come together often in engineering applications. So it is convenient just to combine them. You can combine them, let's say weight, specific weight, or you can just use rho g, which is okay. Any question about this slide? No? Already 10, 15. Weight and equilibrium. I'm just, I already told you that this chapter 1 is, the thing that we need to know to understand, to solve any thermodynamic equation. So many of them are about the assumptions that we make to solve any thermodynamic, the problems. The first one is equilibrium. in reality, not in reality, but when you do a thermodynamic analysis, we assume that our system is in equilibrium. Then maybe if you have this coffee initially, so it is not hot anymore because I bought it about an hour ago. Now, if you want to make it hot, what are you going to do? You can pour some hot water. So if you pour hot water into this cup, what's going to happen is, so it was initially 20, it's pretty not hot enough, then you are pouring hot coffee, boiling, maybe 100. So what's going to happen? It suddenly becomes like, the 90 throughout or 70. Now, initially, you are going to see, where's my bishop? So initially, you are going to see somewhere here is 100, maybe here is 80, down here is 20, here is 60 or 70, etc., right? We don't do any thermodynamic analysis present, in this condition. We wait maybe 1 or 2 minutes for start inside. So that, the temperatures in the cup is going to be uniform. So if you wait, then you get 70, 70, 70, 70, 70, 70, 70, 70, and then surrounding is 20. So now you can put the heat transfer from this coffee to the surroundings. So this is our assumption. When you do a thermodynamic analysis, we assume that our system is in equilibrium. So it has the same temperature. And surrounding air is also uniform at 20 degrees Celsius. Then we can do a thermodynamic analysis to determine the heat transfer from the system to the surrounding. Then some of you may, the question, oh, I don't want to do that. I want to study the heat transfer from this 100 to 80 because there is a temperature difference. Means that there's to be heat transfer. That's no problem. If you want to do that, you can say, oh, this is my system and this is the surrounding, and I want to study heat transfer from here to there. My point is that when you define a system, our assumption is that in this system we have a thermal equilibrium. Okay? And what we study is energy transfer from between a system and its surrounding. Process. Any change that the system undergoes from one equilibrium state to another equilibrium state. So when we do a thermodynamic analysis, means that there is a process. So let's talk about that coffee example again. Okay. So initially we had thermal equilibrium, so 70 degrees Celsius everywhere, and the surrounding is at 20 degrees Celsius. Then we expect that there is heat transfer from this hot coffee to the surrounding air due to the second law of thermodynamics, right? So there's a heat transfer. What is going to happen? Oh, the temperature of the coffee is going to decrease from 70 now down to 60 and down to 50 and etc., and finally it becomes 20 degrees Celsius, right? So when this is a process, initially at the beginning of the process, the coffee was at thermal equilibrium at 70 degrees Celsius. After this cooling process, the temperature of the coffee, reaches 20 degrees Celsius. How many processes do we have? One process, that's the cooling process. From one equilibrium state at 70 to another equilibrium state at 20. So when you have a thermodynamic problem, that means you have a process. In this case, we have one process, cooling process. It is removed from this coffee, and this cooling process, and then this process requires two states, initial state and the final state. Okay, so whenever you do a thermodynamic analysis, you are going to study a process, and to study this process, there are two states, before and after. So we can say initially, T1, this one means state number one was at 70 degrees Celsius, and there was a heat loss. It is removed, and the final temperature T2 is 20 degrees Celsius. So how much heat has been lost can be an example of a thermodynamic problem. Okay. So whenever you define a thermodynamic problem, you are going to define a process, and there should be two states. What about if you have two processes? Then there should be three states. State number one process, state number two, and process number two, and state number three. Make sense? Okay. Yes. So why are we neglecting the enters the container? Why are we not? Like, for example, oh, it's hot. Yeah. If you want to study heat transfer from the coffee to the cup, that's still fine. So in this topic problem, there can be many thermodynamic problems you can create. So for example, I was just talking about the simplest one. So that was this was mine. So I defined this coffee as our system, and the air is our surrounding. And in that case, this cup was its boundary. And your thermodynamic, your problem is also valid. You can say, okay, I have this cup, but now this coffee is my system, and we have an imaginary boundary here, and this cup is our surrounding. Then you can study heat transfer from here to there. And in this case, I neglected this cup and studied heat transfer. So it depends on how you define your system and surrounding. And usually, the mass of the cup is much smaller than the mass of coffee, so you can neglect the heat transfer, to the cup, and then so you can jump through the air. But if you have a, the significant volumes of the cup has this much thickness and a very good insulation, then you need to consider the cup and the surroundings. So you can study. Then there are going to be two processes: coffee to the cup and cup to the air. Okay. And here, we are going to talk about some common process. Earlier, I told you that there are four familiar properties in thermodynamics. They were pressure, temperature, volume, and mass. If you consider that you have a closed system, you can neglect math, then what you have? Pressure, temperature, and volume. So let's talk about pressure, temperature, and volume. Then let's talk about the relation among the three. So let's talk about that. I'm going to increase the pressure of this, not coffee anymore. We talk about coffee too much time. So let's talk about the air in this classroom. Maybe we can talk about AC or so. Now I want to understand the relation between pressure, temperature, and volume of this air. So I'm going to increase the pressure. I'm going to increase the pressure. Then, can you tell me what's going to happen to the temperature? If you increase the pressure of the air in this classroom, what happens to the temperature of the air in the classroom? How many of you think that the temperature goes up? Goes down? It's either direction. It can go up or go down because we have no idea about the volume. Maybe if the volume stays the same, oh, okay, we can say when pressure goes up, temperature goes up. But what about if the volume goes significantly down or goes up? Then what happens to the temperature? We don't know. Because there are three variables. So can you study, this complicated problem? No. So how can we do? We are engineers. What we do as an engineer? We solve complicated problems. Now we change a complicated problem to a simple problem. We change a complicated problem to a simple problem. We are not a scientist. We are engineers. We know how much it costs, that we spend to study a complicated problem. And if we convert to a simple problem with an acceptable error, that could be enough, right? What about if you think about, the energy transfer from here inside the air and outside? Let's assume that this is winter. Outside is very cold, and we want to determine, what kind of capacity heaters we need to buy to maintain 20 degrees Celsius air in this classroom. Then we need to think about heat transfer. Heat is going to move from the air inside to the outside, right? But in reality, in science, heat can move from here to the top, or heat can move here to the wall, or from here to this direction. There can be many directions. Heat can move in any direction. But primary direction is going to be from here to the wall, because outside is cold. So maybe 99% of the heat is going to be this way, rather than going up in parallel or go backward. Then, if you are not hypothesis, we can study heat transfer in this direction or this direction, but 99% of the heat goes this direction. Then, instead of studying three-dimensional heat transfer, as an engineer, I'm going to need the heat transfer this direction or this direction. I'm going to only consider heat transfer in this one-dimensional heat. And you don't have to solve complicated second-order partial differential equations. You can just solve first-order ordinary differential equations because you assume it's a one-dimensional. And the answer is going to be completely different from the actual value. And not because 99% of the field is going to go this way. If you assume that, oh, we need 100 watt, 1,000 watt heater, the correct answer was you just needed 999. You bought 1,000. But you say 20 days of calculation. That's what engineers do, right? In this case, there are three values, but I don't want to study this complicated problem. Then what is going to be a simple solution? I'm going to assume this volume is constant. Let's see what happens to the temperature when pressure goes up. Now you have the answer. When pressure goes up, what happens to the temperature? Goes up. If you don't understand, oh, I'm not sure when pressure goes up and temperature goes up, I'm not sure. I don't get it. Then think differently. When temperature goes up, what happens to the pressure? Let's say that you have, you have this, the coffee. Let's assume that you complete this spin. You heat the coffee over and over. What's going to happen? It's going to explode because of the large volume increase, large because of the high pressure, right? So you can say, oh, when temperature goes up, pressure goes up because of the experience. In other words, when temperature goes up, pressure goes up. That's it. When pressure goes up, temperature goes up. You can simply answer that question by assuming that volume is constant. Can we make this kind of assumption? Yes. If your system is coffee, we can assume that coffee is liquid. So the volumetric change of the coffee can be negligible. That is called isochoric process, a process during which the specific volume V remains constant. When volume is constant, it is called isochoric process. Or you can just say constant volume process, and you can simply think of this question: when pressure goes up, temperature goes up. When pressure goes up, temperature goes down. If you still don't get it, just think about some funny example. When you're walking on a street and there's some stranger coming towards me and just throw a punch on my face. And I have a pressure on my face. Then what do? I get pissed off. The temperature goes up. So when pressure goes up, temperature goes up. Make sense? Now you don't forget that, right? Let's talk about something else. Oh, now I'm not going to talk about this problem anymore. Let's forget about this pressure, and I'm going to give you another example with the pressure, temperature, and volume. Now, I want to study when temperature goes up, what happens to the volume? Can you answer that question? No, now you know the answer. We cannot answer that question because we have no information about pressure. Then if you want to solve it simply, you can say, oh, I think pressure remains constant. Then, when temperature goes up, what happens to the volume? Goes up. Now you know the answer. How do we know when it goes up? Think about, what is the thing that it's not the old version of the flying the pool that you hit air inside this balloon and it goes up. Yeah. So temperature goes up, volume goes up. But is there many the examples where we can consider pressure? Yes. In this classroom, what is the pressure here? 100 kilopascal. What is the pressure near the door? 100 kilopascal. What is the pressure outside? 100 kilopascal. Unless, what about if you go to the second floor? 100 kilopascal. Unless this engineering technology building is as tall as Sears Tower in Chicago, that if you move from first floor to the 100th floor, then there is a pressure difference. But from here to the second floor, not much. So you can assume that it's a constant pressure condition. So within this classroom, you can say when temperature goes up, volume goes up. When temperature goes down, volume goes down. That is called isobaric process, a process during which pressure P remains constant. Okay, the last one. Now you know what's coming, right? Pressure, volume, and temperature. Now we want to study when pressure goes up, what happens to this volume? We know the answer. I don't know, right? Unless we have information about the temperature. So the simplest answer is that I'm going to assume temperature remains constant. When temperature remains constant, then what happens to the volume? When pressure goes up, volume goes down. Then, is it common to have a constant temperature process? Yes. What about in this classroom? If I have this, a cup of coffee, if I pressurize that, what happens to the boiler? Goes down. Is there a significant temperature change? If you pressurize it, it becomes boil again. That's called magician, right? I'm not. So even though you pressurize it, the temperature doesn't go up that much. Of course, in a laboratory, if you extremely increase the pressure, then temperature may go up. But in general, now, right? You can neglect the temperature difference. Then you can study pressure volatility. So that is called isothermal process or constant temperature process. Those three processes are pretty common in thermodynamics. So whenever you have a thermodynamics problem, maybe you can, if there is a the enough information, you can assume one of the three processes, then the solution would be pretty simple. On cycle, a process during which the initial and the final states are identical. So when you have this piston, then the device, let's assume that you have an expansion process here. Piston is expanding. And then now, you have a compression process. So the piston goes to the initial, the position. Then these two processes, expansion, compression, all together, it becomes a cycle. Any question about this slide? I know it's kind of boring, but consider that this is, I already told you, it's the chapter 1. You're still learning how to, to study thermodynamics. Okay? The last slide before we talk about temperature and pressure. Okay, the first one is important. Steady and unsteady or transient. There are, the steady problems and unsteady problems. What makes it steady problem, meaning is that things doesn't change in time, then it is a steady problem. If, the properties change in time, that means unsteady or transient problem. Then, if I have a hot coffee right here, holding it, and then heat is transferred from this coffee to the surroundings, is it a steady problem or an unsteady problem? Unsteady, because the temperature, which is a property of this coffee, goes down in time. So right now, 70, 10 minutes later, 60. So there is a change in time. Then it is an unsteady problem. So let's talk about this AC system. The air in this classroom remains constant. The temperature of the air in this classroom remains constant, right? So right now, about 20 degrees Celsius. Maybe 5 p.m., it's going to be 20 degrees Celsius. The AC is keep running just to maintain constant temperature inside. Then it is a steady problem. Usually, when we have a closed system, they are unsteady problem. And open system, one are steady problem. So we are going to study unsteady in chapter 3 and heavy in chapter 4. Of course, there are some unheavy open systems, but the majority of open system problems are heavy problems. The zeroth law of thermodynamics is pretty simple to understand. Any question about this slide? No. You're almost to the end of chapter 1. Isn't it exciting that that you're waiting for the fun chapter 3, right? No, not yet. So the next slide is temperature. So we usually have 2 points. The first one is ice point. The other one is steam point. Ice point is when water becomes ice, right? Not necessarily, because this ice point depends on the pressure. But in general, at 1 atmospheric pressure, which is the pressure in this bathroom, ice point is around 0 degrees Celsius. So in a stationary system, we assume that water ice point is 0, water boiling point is 100. That's how we define stationary system. On the other hand, Fahrenheit system, we assume that ice point is 32 and the boiling point is 212. That's how we define temperature in Fahrenheit. Then how can you convert between Celsius and Fahrenheit? It's pretty simple. How many degree Celsius between ice point and steam point? 100. So the change, the delta change in temperature, this means change or difference in temperature, right? Change in temperature is 100 degrees Celsius. Then what about the change in temperature in Fahrenheit? 212 minus 32, so 180 Fahrenheit. So what is the ratio between these two? 100 divided by 180 is going to be 5/9. So the ratio between Celsius and Fahrenheit is going to be 5/9. So if you want to convert between Celsius and Fahrenheit, you use this ratio. So if you have a Fahrenheit, you use this ratio, 5/9. Then it becomes Celsius. However, with one condition. The starting point, the reference point, which is the ice point, is not 0. The ice point of Fahrenheit is 32, so you need to add 32. I'm going to subtract 32. Then that's how you convert between Celsius and Fahrenheit. The other way, Celsius times the inverse of this one, 9/5. Now we need to add this one, the reference point, that becomes Fahrenheit. Then this one is English unit. Then is it the SI unit? No. Celsius is not SI unit. Then what is SI unit? Kelvin. SI unit is going to be Kelvin. What is the how can we get Kelvin from Celsius? Very simple. We assume that ice point in Kelvin is 273.15 or 16 Kelvin is the ice point. You can just say 273, which is fine. We are engineers, we're not a scientist. This one is fine. Then what is the boiling point? 373 Kelvin, which is 100 degrees Celsius. Oh, wait a minute. The change in Kelvin is 100. The change in Celsius is 100. So 1 degree Celsius increase is the same as 1 degree Kelvin increase. So they're not much different. Then why do we use Kelvin? Because the change in Kelvin, the change in Celsius are the same, right? Because there is one interesting science meaning, which is that when every system has thermal energy, this coffee has thermal energy. That's why it has temperature. So it was initially 70 degrees Celsius. Some of the thermal energy has been lost due to heat transfer to the surrounding. The temperature went down. What if you completely remove thermal energy? If you remove thermal energy, temperature goes down, right? If you add thermal energy, temperature goes up, right? What about if you completely remove thermal energy? So there's no more thermal energy left over in the coffee. What's going to be the temperature of the coffee? When there's no thermal energy, the temperature of the coffee is going to be minus 273.15 degrees Celsius. Yeah, that is 0 Kelvin. So that is 0 Kelvin. Not okay, the 0 Kelvin. So when some scientists say that, oh, I invented a new cooling machine that we can go down to minus 500 degrees Celsius, impossible. Because the lowest possible temperature is 0 Kelvin. Okay? Well, the Kelvin has a science meaning, so we use Kelvin as our standard SI unit. So that's everything about temperature. And on Thursday, on Tuesday, next week, after you cross the bridge, you go there. No? Then we are going to talk about pressure. You don't know that every morning that people cross the bridge. No? I will go there. I will go there with you. All right. That's all. Thank you.